Hi class, we continue our study in chapter 14 by moving into section 14.3, talking now about what a partial derivative is, okay? So I'm going to start with the definition, okay? If f is a function of two variables, its partial derivatives, okay? So notice now this is going to be a little bit different from Calc 1. In Calc 1, when you had a function of a single variable, you had find its derivative, its single derivative. So now if you have a function of two variables, we don't say find the derivative, we say find the partial derivatives. And here, if you have a function of two variables, you have two partial derivatives, okay? And these derivatives are denoted f with the subscripted x and f with the subscripted y. And we can find these derivatives, these partial derivatives, by just simply using the limit definition of a derivative all the way back from Calc 1. So the partial derivative of f with respect to the x variable is the limit as h goes to 0 of f of x plus h comma y minus f of xy over h. Notice here that the h is only attached to the x part here in this function. It looks like y is not changing. Y is staying constant. The flip side here, the partial derivative of f with respect to y is the limit as h goes to 0 of f of x comma y plus h minus f of xy over h. It looks like only the h part here is attached to the y variable. So we're holding the x constant. That's an important thing to remember. All right, so there are many alternative notations for this partial derivative. For instance, instead of the partial derivative of f with respect to x, we can write f1 or capital D1f. This means differentiate with respect to the first variable. Or this is the most common notation that we'll use. The partial derivative of f with respect to the x variable, okay? So it's really important here that these partial derivatives cannot be interpreted as the ratio of differentials. That's not what we're seeing here, okay? So here's some additional notation for partial derivatives. The most common one, though, that I will lean on in this class is either this notation here, f with the subscripted x, that's telling us the partial derivative of the f function with respect to x, or this notation here, the partial derivative of f with respect to the x variable. Okay, you can flip it around with y as you see down here, and so on, depending on how you classify your variables. All right, so to compute partial derivatives, this is important. All we have to do is remember that the partial derivative with respect to x is just the ordinary derivative of the function g of a single variable that we get by keeping y fixed. That's it. So to find the partial derivative of x, of this function with respect to x, just remember all you're doing is keeping y fixed. You're treating y like a constant. All right. And the same thing here. If you want to find the partial derivative of f with respect to y, you're just going to keep x as a constant and differentiate this function with respect to y. That's it. Okay. So if whatever partial derivative you're finding, just hold the other variable constant. That's the key thing to remember here. All right. So let's do two examples here, or an example here that has two parts. I've got this two variable function f of xy. It's equal to x cubed plus x squared y cubed minus 2y squared. I want to find the partial derivative of x evaluated at 2, 1, and I want to find the partial derivative of y evaluated at 2, 1. Okay, so holding y constant and differentiating with respect to x, this is what we get. F of x, okay, or f partial derivative of x, you look at the first term, 3x cubed. That's derivative is 3x squared. You go to here, x squared y cubed. You're going to treat y cubed as a constant, so the derivative of x squared is just 2x. Now when you get to this term, minus 2y squared, you're treating it as a constant. So what's the derivative of a constant? It's 0. So this is the partial derivative of this function with respect to the x variable. So now to evaluate this, just plug in 2, 1. Plug in the 2 for the x, 1 for the y, and you get 16. Similarly, if I want to find the partial derivative of f with respect to y, you're going to hold x constant. Hold x constant. Excuse me. So the partial derivative of f with respect to y of x cubed, well, holding x as a constant, that goes away, that's 0. This x squared is the constant, so the derivative of y cubed is 3y squared. And similarly, the derivative here, you bring down the 2, you get minus 4y. Plugging in 2, 1 here, and you don't get 16. Notice when you plug in and do this arithmetic, you get 8. And that's okay. You don't necessarily have to get the same value here. All right, so how do we interpret these partial derivatives? What does it mean? Okay, so to give a geometric interpretation of partial derivatives, we recall that the equation z is equal to f of xy represents a surface S, so basically the graph of this function, okay? If f of a comma b is equal to c, all right, then the point ABC lies on this surface, okay? So now, here's what we're going to do. By fixing y constant, y is equal to some value b, we are restricting our attention to the curve C1, okay, which is the vertical plane y is equal to b where it intersects our surface. So in other words, C1 is the trace of S in the plane y is equal to b. So looking here, C1, S is our surface, okay? C1 is this curve right here. It's just the trace along the top here, this blue curve where y is equal to b, okay? Likewise, if we look at the vertical plane, x is equal to a, all right, just holding that plane constant, where that intersects this surface is this curve C2, okay? And notice that both of these curves, C1 and C2, pass through the point P, okay? They're different curves, right, because you're intersecting the surface differently, but they both intersect at that point ABC. All right, so note that C1 is the graph of the function f of x comma b. So the slope of its tangent, which we'll call T1 on the point, is its derivative. So it's our partial derivative, all right, evaluated, partial derivative with respect to x evaluated at that point. Same exact deal here, okay? The curve C2 is the graph of the function, we'll call it g of y. So its slope here is just the derivative, the partial derivative of the function with respect to y, evaluated at that point AB. That's it. That's it. Okay, so thus the partial derivatives can be interpreted geometrically as the slope of the tangent line to that points, to the traces of these curves C1 and C2 of S. Okay, in these two planes, y is equal to b and x is equal to a. So partial derivatives can also then be interpreted as the rate of change. So if z is equal to a function of xy, then the partial derivative of z with respect to x represents the rate of change of z with respect to x when y is fixed, when y is constant, remember that. The partial derivative of z with respect to y represents the rate of change of z with respect to y when x is fixed. Okay, so here, you're looking at the rate of change along this C1 curve. Here you're looking along the rate of change along this C2 curve. That's what the partial derivatives are telling us. All right, let's do an example. If f of xy is equal to 4 minus x squared minus 2y squared, let's find the partial derivative of x evaluated at 1, 1 and the partial derivative of y evaluated at 1, 1 and interpret these numbers as slopes. Okay? So we can very easily see that the partial derivative of x, the partial derivative of f with respect to x is just minus 2x because that and that is constant. The partial derivative of y, or the partial derivative of f with respect to y is just equal to minus 4, or minus 4y, excuse me. So plugging in the point, the value is 1, 1. The partial derivative of f with respect to x is minus 2, and the partial derivative of f with respect to y is just minus 4. So the graph of f is this shape here, and its z is equal to 4 minus x squared minus 2y, and the vertical plane y is equal to 1 intersects this parabola, z is equal to 2 minus x squared, comma, where y is equal to 1. All right, as in the preceding discussion, we labeled it C1. Okay, so the slope of the tangent line here of this parabola at this point 1, 1, 1 is just negative 2. You can see it right here. Similarly, here, you got this shape when you look at the plane xy intersects this shape that we're seeing, and it's the parabola z is equal to 3 minus 2y squared, where it's intersecting the plane x is equal to 1, and the slope of this line here is negative 4. That's all we're saying. So the slope of the tangent line at that point is -4. Okay, when you're going along the plane x is equal to 1, that's important. All right, let's go on just real briefly talk about functions of more than two variables. So this partial derivative can be extended for 3 or more variables. It doesn't matter. Okay, it could be 5, it could be 10. You treat it exactly the same way. So you just you just hold all the other variables constant. That's it. Okay, so here you can just see a more formal definition in which there are n variables here. If you want to find the partial derivative of the 5th variable in there, okay, x sub 5, you just hold all the other variables constant. That's it. All right, so let's try this one. Let's find f of x, the partial derivative of f with respect to x, with respect to y, and respect to z, if our function is of 3 variables, and it's listed as, and the function is equal to e raised to the xy power times the natural log of z. All right, so to find the partial derivative of x, hold y and z constant. Okay, so then you take the derivative here. This would be like e to the 5x. Well, you'd bring down the 5. So here you just bring down the y times e to the xy. Natural log of z is just a constant. Same thing with the partial derivative with respect to y, except you bring down the x. And here the partial derivative with respect to z, this exy is a constant, so you're going to hold that constant, and then the partial derivative of the natural log of z is just 1 over z, and that's it. All right, let's talk now about higher derivatives. So this is like taking the second and third derivative here. If f is a function of 2 variables, then its partial derivatives with respect to x and with respect to y are functions of 2 variables. So we can consider their partial derivatives a little bit more here. These are the second partial derivatives. You take the partial derivative of f with respect to x a second time. Here you find the partial derivative of x, and then find the partial derivative of that with respect to y, and so on. These are called the second partial derivatives of f. Okay, and we use just the following notation here. It's the same basic notation here that you would use with Calc 1 derivatives here when you find higher order derivatives here. All right, so here's just some more additional notation for this. So suppose we have this one here, this partial derivative of f with respect to xy. This means we first differentiate with respect to x, and then we differentiate with respect to y. Okay, so here when you have this notation, do this one first, then this one. Here it's just like in Calc 1. You're going from right to left though in the denominator. You differentiate with respect to x, and then you differentiate with respect to y. All right, so if I ask you to find the partial derivative of f with respect to yx here, you're just going to differentiate here with respect to y first, then x. All right, let's find this. Let's find the second partial derivatives of this. Okay, so we have this function f of xy, and it's equal to x cubed plus x squared y cubed minus 2y squared. All right, we found this already. Okay, the partial derivative with respect to x of this is just 3x squared plus 2xy cubed, and the partial derivative with respect to y here is just 3x squared y squared minus 4y. So if I want to find the partial derivative of this function with respect to x twice, you're just going to take the partial derivative of our first function here and differentiate it again with respect to x. So here this becomes 6x. Here, what's my variable here? It's just x, so the 2y cubed is a constant. And it's similarly, you can verify the rest of these on your own. These are the rest of the higher order partial derivatives.